In this video, I will be talking about classification of dynamical systems, which in this particular case, represented by two-dimensional maps. So, classification of dynamical systems. So here we consider case of 2D maps. So what we found on the last lecture when we were considering Helen's map, that in 2D maps we can have chaotic regimes. And then the next question would be when we can observe them. When we can observe them. And to answer this, we first make classification of dynamical systems, and then first is classification. And dynamical systems. And second is investigating of sensitivity to initial conditions. So these two problems are closely related, but today I will be talking about classification of dynamical systems, and about sensitivity we will talk next time. So what in both cases we will consider to analyze both these stories. We will analyze trajectories of nearby orbits. So the idea with the classification is like this. We have a point in two-dimensional space. Let's say position vector is Rn. And well, and then after we applied map, we get new point, which is position vector Rn plus 1. And assume we have another point with position Rn plus epsilon, small vector epsilon n. And this will go to another place, this position Rn plus 1, after we applied map, plus epsilon n plus 1. It's another vector. And the question here, so we have two orbits, R0, R1, so on, Rn, and so on. And we have another orbit, which is R0 plus epsilon naught, R1 plus epsilon 1, so on, Rn plus epsilon n. These are vectors, all of them vectors, and so on. And the question is how epsilon n, this small vector, is changing. So this vector tells us whether these two orbits converge, diverge, or stay nearby, just stay nearby. So this kind of behavior of epsilon n, whether it increasing, decreasing or not, is related to sensitivity to initial conditions, obviously, but it's also used to make classification of dynamical systems. For classification, it is represented like this. So we have our plane, xy plane. So we have this Rn position vector, and assume we consider some area around Rn. We will call it An. So that after one iteration, our position vector is Rn plus 1, and this area An deformed to, so this shape AN deformed to another shape, AN plus 1, which has different area. And therefore, we can check what happens to areas. So originally, it was some domain with area A0, then it went to A1, so on, AN, and so on. So the question here, if what happens with area AN, if N is increasing, the map is called area increasing map. The map is area increasing. Then if AN is not changing, then the map is called conservative. And if AN decreasing tends to 0, then map is called dissipative or area decreasing. So this is general classification of maps. So if map is area increasing, then we can't observe chaos because our solutions become unbounded, and we remember even from one-dimensional maps that unbounded orbits, not chaotic. And what we will do now, we will try to find out how to analyze how this area is changing. The result you're supposed to remember is that AN plus 1 equals to determinant of Jacobian at Rn by absolute value times AN. So Jacobian is derivative of f over x at Rn, derivative of f over y at Rn, derivative of g over x at Rn, and derivative of g over y at Rn. So this is for the map Rn plus 1 equals to f over n and g over n. So this is our map. And so this is what I want to prove. To prove this, people use two approaches. One approach is to consider change of area of parallelogram. So let's say if, so this is Rn, let's consider, if we will consider a rectangle here, rectangular shape, then after one iteration, it will not stay rectangular, it will rather transfer into parallelogram. And so to avoid this transition, we can here consider already. So here could be also parallelogram. Then it still will go to parallelogram, transfer to parallelogram. And this is probably first statement I want to prove. Parallelogram. Parallelogram transfers into parallelogram. So this is first statement. In fact, another approach would be to consider, not to consider parallelograms, but rather ellipses. Ellipse also transfers into ellipse as a first approximation for the maps. So this is what I want to prove now. And to prove this, I will start with simpler problem. So we have point with position vector Rn and point with position vector Rn plus epsilon n. So now after one iteration, this transfers into the scenario when Rn went to position Rn plus 1 and Rn plus epsilon n will shift here. So this will be another vector. Rn plus 1 plus epsilon n plus 1. So what we want to find out, we want to find how vector epsilon n plus 1 depends on epsilon n. So what we have Rn plus 1 equals to f of Rn, g of Rn, and Rn plus 1 plus epsilon n plus 1 will be equal to f of Rn plus epsilon n, g of Rn plus epsilon n. So this is from definition of our map. And let's consider now, so what we can put Rn. Let's present it as a vector with components x and y n, and epsilon n, a vector with components epsilon, say xn, epsilon yn. Then xn, from here we will get xn plus 1 plus epsilon xn plus 1 will be equal to f of Rn plus epsilon n. Yeah, because what we took here first equation. So here we have two equations, vector equation, which has two scalar equations for x component and for y component, and this is this equation only for x component. Let's check what it will be. So again, xn plus 1 plus epsilon xn plus 1 equals to f of Rn plus epsilon n. This can be represented as, we can take linear approximation for this around Rn. So this will be f at Rn plus derivative of f over x times x component of epsilon n plus derivative of f over y times y component of epsilon n. Now this xn plus 1 equals to f of Rn. This is from definition of our map. Therefore this cancels and we get epsilon, x component of epsilon is derivative of f over x, epsilon and x plus derivative of f over y, epsilon and y. And similarly, epsilon y and y component of epsilon will be, so same kind of procedure will show that it will be similar expression, but instead of f, we will have g derivative of g over x times epsilon and x plus derivative of g over y times epsilon and y. And from these two, we can put it like this: epsilon n plus 1 vector with these two components equals to Jacobian at Rn times epsilon n. So Jacobian, where Jacobian at Rn is derivative of f over x at Rn, derivative of f over y at Rn, derivative of g over x at Rn, and derivative of g over y at Rn. So this is very important formula to remember. So this formula to remember. And this is definition of Jacobian. We've seen this before. Now let's consider parallelogram. So this is our vector Rn. And here, let's say we have a parallelogram. Parallelogram means, for example, this side is epsilon n vector. This side is vector delta n. If it's parallelogram, this side equals to this, therefore it's epsilon n also vector. And this equals to this, therefore this is also delta n vector. Now, after one iteration, we get, so this position vector gets to Rn plus 1. Now this will be delta n plus 1. This vector will be epsilon n plus 1. And what is important, since this vector is, so this vector is also epsilon n, and its image will be vector epsilon n plus 1 in first approximation. And this vector will be delta n plus 1. In first approximation, let's put it like this: Jacobian at Rn is equal, let's say roughly equal to Jacobian at Rn plus epsilon n, and roughly equal to Jacobian at Rn plus delta n, because epsilon and delta are small. And therefore, parallelogram transfers into parallelogram. So now let's find area of first parallelogram, AN. Is this area equals what we know? So if this is, say, some angle theta, this will be equal to length of vector epsilon n times length of vector delta n times sine of angle between them. And this can be represented as length of vector cross product of epsilon n and delta n. So this is pretty much definition of cross product. Now, vector epsilon n has components. So cross product is defined for three-dimensional vectors. Therefore, we will have first component is epsilon n x, second component is epsilon n y, and third component is 0. Same is delta n. So third component, it's perpendicular to the plane, which we consider. Delta nx, delta ny, and 0. And therefore, this cross product, epsilon n, delta n, it's again from the definition of cross product, it will be the determinant of matrix. With entries here we have unit vectors I, j, and k. Here will be epsilon n x, epsilon n y0, delta n x, delta n y 0. And this will be equal to unit vector k times epsilon nx delta nx minus epsilon n, sorry, here y, epsilon ny delta nx. And therefore, an is length of this vector times delta n, and this will be equal to epsilon nx delta ny minus epsilon ny delta nx. And same we can say about an plus 1. This will be equal to epsilon n plus 1x delta n plus 1y minus epsilon n plus 1x times delta n plus 1y. So what we found out earlier is epsilon n plus 1x is derivative of f over x at Rn times epsilon nx plus derivative of f over y at Rn times epsilon n y. And same with, okay, epsilon n plus 1y will be g of 1x Rn epsilon nx plus derivative of g over y at Rn times y component of epsilon. And same would be with delta n plus 1x and delta n plus 1y. So the only difference will be here will be delta nx, delta n y, and here's the same. And if we put all of this here, I'm skipping this part, then we can find out that this will be equal to Jacobian at Rn sorry, this is what we will have here is determinant of Jacobian at Rn times an. So this is, it should be by absolute value everywhere. So this is what we will prove. And last piece is this. So what we have proven, an equals to determinant of j at Rn minus 1 by absolute value times an minus 1. On the other hand, for an minus 1, so determinant of j at Rn minus 1. And here, this will be equal to determinant of j at Rn n minus 2 times a n minus 2. So, and so on, and at the end we will have this product of determinants. It will be determinant of G R, so here minus 1, R n minus 1 times determinant of G R n minus 2 times so on times determinant of G at R naught times A naught. And this can be written like, so this should be by absolute value. This can be written, so we know the determinant of product of determinants equals to determinant of product. Therefore, this determinant will be of J at Rn minus 1, so Jacobian times Jacobian Rn minus 2 times so on times Jacobian at R naught. So value of this determinant times A naught. Or we can put it like determinant of some matrix J, let's say J total times A naught, where J total is product of these determinants along the path. Now the question is what happens to this determinant of J t. So whether it tends to infinity, 0, or stays at some fixed value, yeah. So this would be area expanding. This would be dissipative. And this would be conservative. So next question now with areas, what happens to the shape of area? So we assume we had this A and, or say A naught, it was this. Then we, after n iterations, this can get, so for example, so here it can be elongated and elongated, for example, like this. So this shape is changing. And the next important point is change of shape. And this is answered by Lyapunov exponents. And I will talk exponents, and I will talk about them on the next lecture.